Okay, so Maggie and I decided to do population growth models. Not only does it relate to calculus, but we found it interesting because it also relates to the increase of population that our world is currently facing today. And this is an important topic for both of us, so we just wanted to know more about it and understand it better and how it relates to calculus. So we start off with a differential equation, and that is dp over dt equals kp. So dp over dt is the growth rate of a population in a given instant. T is time, k is the per capita rate of increase, and p is population size. So the population and the rate of growth of the population are proportional, and this is something to keep in mind for later. And it basically means that as the population grows, so does the rate of its growth because there are more people that are reproducing. So here's our original equation, dp over dt equals kp. And like any differential equation, we want to get all the p's on the same side. So first we can multiply by dt. So when we do that to both sides, we're left with dp equals kp dt. Then we can divide both sides by p, and we get 1 over p dp equals k dt. Next, we want to take the integral. So the integral of 1 over p dp equals the integral of k dt. And when we take the integral, we're left with the natural log of the absolute value of p equals kt plus c. Then we want to raise the right side to e to get rid of the natural log, and we're left with the absolute value of p equals e to the kt plus c. Then we can separate it, and we have the absolute value of p equals e to the kt times e to the c. And e to the c is a constant, so we can replace that with just the letter c. And because c can be positive or negative, because it's a constant, we can get rid of the absolute value sign, and we have p equals c times e to the kt. So here's our final equation, p of t equals c times e to the kt. Now to go a step farther, and this will be important in the next example, we can find population initial by plugging in 0 for time. So when we do that, we have p of 0 equals c times e to the k times 0, and k times 0 is 0, so we have c times e to the 0, and e to the 0, like any number to the 0 power, is 1, so p of 0 equals c times 1, and c times 1 is just c, so the population initial, or population at time 0, is c. And so we can plug that back into the equation from the top, and we have the population at time t is equal to the initial population times e to the kt. So the first example is this. The table below shows the rabbit population on an island where t is the number of years beginning at the year 2000. So A, determine the relative growth rate or per capita rate of increase, which is k. B, write a general equation for the population of p of t. C, estimate the population in 2010. And D, how many years will it take for the population to double? So for part A, determining k, we can use the equation we found before, which is p of t equals p sub 0 e to the kt. So we can pick any data point from the graph, but we can just pick the first year, so the year 2001, and we can plug 1 year into our time, and we can replace the initial population with 1,500, which is the population of the year 2000. So then we have p of 1 equals 1,500 times e to the k times 1. So then we can replace p of 1 with 1,577, which is from the chart, and then we can divide both sides by 1,500, because remember we're trying to find k. So then k times 1 is just k, and 1,577 divided by 1,500 is 1.0513 equals e to the k. So then we can take the natural log of both sides, and we have the natural log of 1.0513 equals natural log of e to the k, and our log powers, or log rules, tell us that we can bring the k to the front. So we have the natural log of 1.0513 equals k times the natural log of e. And the natural log of e is just 1. So then we have 0.05 equals k. So for part B, we're writing a general equation for the population of P of t. So we take our final, or our original equation, which is P of t equals c times e to the kt, and we can plug in our k and our initial population. So P of t equals 1,500 times e to the 0.05 t. So for part C, we want to estimate the population in 2010. So for our time, we'll plug in 10, and we'll use our equation from the last slide, which is this. So when we do that, we have P of 10 equals 1,500 times e to the 0.05 times 10. And we can plug that right side of the equation into our calculator, and we get P of 10 equals 2,473 rabbits. So in the year 2010, there will be 2,473 rabbits on the island. So for part D, we want to find how many years it will take for the population to double. So using our equation from 2 slides back, this one, we can plug in the double population, which is 3,000. So 3,000 equals 1,500 times e to the 0.05 times t, and we're trying to find t. So we'll divide both sides by 1,500, and that leaves us with 2 equals e to the 0.05 times t. Then we can take the natural log of both sides, and like our log rules state, we can bring the 0.05 times t out to the front. So then we have the natural log of 2 equals 0.05 times t, the natural log of e. And like before, the natural log of e is 1. So that leaves us with the natural log of 2 equals 0.05 times t. And since we want to find t, we can divide both sides by 0.05. So the t equals the natural log of 2 divided by 0.05. And so the time it takes for the population to double is about 13.86 years, or if you round up, 14 years.
One example is, Nadia owns a chain of restaurants that operated 200 stores in 1999. There are 2 parts to this problem. A. How many stores did she operate in 2007 if the rate of growth is 8% per year? And B. How many stores did she operate in 2007 if the rate of growth is 10% per year? So first, we're going to tackle the first part, A. So we're going to define each thing that is in our equation. So P of t is going to be the number of stores total. T is going to be the number of years between 1999 and 2007. I wrote it incorrectly, but that's going to end up being 8. K is going to be our rate of growth, which is 8%, which is going to translate to 0.08. And our P initial is 200 because she started out with 200 stores. So there's our equation. And now we're just going to plug our variables in. So we end up with P of t equals 200 times e to the 0.8 times 8. From here we can simplify and we get P of t equals 200 times e to the 0.64. We plug that into our calculator, and we get P of t equals 379.29. This means that she operated 379 restaurants in 2007 if the rate of growth was 8%. We know that we have to round down from 379.29 to 379 because she can't operate only 0.29 of a store. Therefore, she only operated 379. Now for part B. Pretty much everything is going to be the same. The only thing that's going to change is our K. So P of t is still going to be number of stores total. T is still going to be the number of years between 1999 and 2007. Again, that's written wrong, but it's still going to be 8. Our K is going to be 0.1, because it's 10%. And our initial P is going to be 200 as well. So here we are just plugging it into the formula. Here's our formula, and here it is plugged in. So we get P of t equals 200 times e to the 0.1 times 8. From here we can simplify it even more, and we can say P of t equals 200 times e to the 0.8. If we plug that into our calculator, we get P of t equals 445.11. This translates into 445 restaurants. She would have operated 445 restaurants in 2007 if the rate of growth was 10% per year. Again, we have to round down from this 0.11 because she cannot run only a fraction or a part of a store. So another example. The number of dogs on an island grows exponentially, and the number of cats on that island decays exponentially. Initially, there are 100 dogs and 600 cats. After 2 years, there are 400 dogs and 200 cats. At what time did the dog population overtake the cat population? So, in order to solve this problem, the first thing we need to do is put these into equations and out of words. So, rewriting what the problem said, at time equals 0, d of 0 equals 100 because there are initially 100 dogs. C of 0 equals 600 because there are initially 600 cats. At t equals 2, d of 2 is going to equal 400 because there are 400 dogs after 2 years. And C of 2 is going to equal 200 because after 2 years there are 200 cats. So now we are ready to start the problem. Here's our equation again. One thing to keep in mind is that this time we're going to have 2 variables. One of them is going to be exponentially growing, and the other one is going to be exponentially decaying. In order to keep them straight in our mind, we have to remember that when k is greater than 0, it's going to signify exponential growth. When k is less than 0, it's going to signify exponential decay. So, writing our equation again, we know that d of t equals 100 times e to the k1 times t. This is the function for the dogs. So we know that k1 has to be greater than 0 because we know they are exponentially growing. Similarly, c of t is going to equal 600, because that's the initial, times e to the k2 times t. And we know that k2 has to be less than 0 because we know from the problem that the number of cats is exponentially decaying. So, now in order to solve this problem, we're going to look at time equals 2. So, we're going to plug in 2 for t. d of 2 equals 100 times e to the k1 times 2. So we're just changing this. This used to be a t, we're just changing it to 2. And we're doing the same thing here. C of 2 equals 600 e times k of 2 times 2. So, we also know from the problem that at time equals 2, there are 400 dogs. And at time equals 2, there are 200 cats. So, what we can do is we can set this part of the equation equal to this part, and the same thing with cats. This way we can begin to solve for k1 and k2. First, we're going to start with the dogs. So all we did here was I rewrote the equation. So 100e to the k1 times 2 equals 400. From here, we can solve this by first dividing by 100 from both sides. So we end up with e to the k1 times 2 equals 4. From there, we can do the natural log of both sides, which will leave us with k1 times 2 equals ln of 4. Then we divide by 2 from both sides. When we plug that into our calculator, we get that k1 equals 0.693. If we remember correctly, the dogs are exponentially growing, so k has to be greater than 0, which it is, so this could be the right answer. Next, we're going to move on to the cats. We're going to do the same thing. All I did was rewrite the equation. 600 times e to the k2 times 2 equals 200. Here we can solve. We divided both sides by 200, and then again by 3 here. Then we took ln of both sides and ended up with k2 equals 1/2 ln of 1/3. When we plug that into our calculator, we get that k2 equals negative 0.549. We remember that k2 is supposed to be less than 0 because the cats are exponentially decaying, so this also could be the correct answer. Now what we have to do is we're plugging them back into the equation, back into our initial equation. So we have for dogs, we have 100e times 0.693, our k, times t. And for cats, we have c of t equals 600 times e to the negative 0.549, which is our k, times t. Since we want to figure out where the dog population overlaps the cat population, we want to find where they are equal. So we're going to set them equal to each other, just like this. So now all that we have to do is we're going to solve for t so we can find the time. So we divided by 100 and then divided by e to the negative 0.549 t. That way we have all of this on one side and just the 6 on this side. From here, we can do ln of both sides. And then we can factor out a t from both sides. And then divide by all of this stuff on the inside to get what our t is going to be. Now all we have to do is plug it into a calculator, and we get that t is approximately 1.44 years. So that means after about 1.44 years, the dog population will overlap the cat population. If we want to check our work to see if it makes sense, all we have to do is graph. So we know that the dogs start at 100. This is time 0. We know that the dogs start at 100, and at time 2 are at 400. Similarly, we know that the cats start at 600 at time 0, and at time 2 end at 200. So just drawing a graph and roughly estimating, it seems like this could be our correct answer because it falls about halfway between 1 and 2. So 1.44 would make sense. Now we have a homework problem for you. The homework problem is, a country's population in 1994 was 107 million. In 1997, it was 112 million. Estimate the population in 2008 using the exponential growth model. Round your answer to the nearest million. And thanks for watching.